Energy Management specializes in motors, drives, and generators, as you can see there. And because of the drives, we got into the power quality aspect. So we do lots with harmonics, power factor, infrared, surge protection, and of course, arc flash. So today's presentation is going to basically be a beginner's presentation, but I want to take some special time to talk about changes that have occurred in the arc flash standard since maybe 2009. And I think that there will be some interesting things, even if you are quite familiar with arc flash. If you're not familiar with arc flash, we will try to cover it in a pretty brief manner, but in a sufficient detail that you can understand it. Our regular arc flash class is 8 hours, so obviously between this week and next week, we're going to have to move fairly quickly. Next week is what I would call more of an advanced class. We're going to talk a lot about arc flash mitigation, how to lower your calorie levels on arc flash, and we'll talk about a lot of subjects such as the requirement for available fault to be printed, the requirements for breakers and fuses to be coordinated for arc flash protection, and so on and so forth. So next week we'll be much more in depth, but let's get going on this. Now, this is a variable frequency drive cabinet. I'm going to say it's 480 volts. You can see a drive there in the upper left, and then we have a harmonic filter, circuit breaker, so on and so forth. I just want you to think of this as a 480 volt panel. Now, in order to start this drive up, we are going to have to open that door. We're going to have energized parts in there. What do we need to wear? Well, for the purposes, I know a lot of you know this, but for the purposes of this presentation, I'm going to assume that we don't know. And so we're going to come back to this slide close to the end of our presentation and talk about it again. What is an arc flash hazard? This is NFPA 70E. It is in the definition section. If you haven't spent a lot of time in NFPA 70E, NFPA 70, as you know, is the National Electrical Code, and Article 100 is the definition section. In NFPA 70E, Article 100 is also the definition section. So they say an arc flash is a source of possible injury or damage to health associated with the release of energy caused by an electric arc. I like pictures, so to me, this is an arc flash. Now, I want to talk about short circuits for a moment. The short circuit current is in many ways proportional to the size of the transformer. So in that way, the amount of electrical current that can flow is similar to the amount of water that could flow, depending upon how open that faucet is. So let's take a look at a transformer. I'm going to select a 150 kVA transformer. It's 240 volts, and the impedance is 5%. That impedance is a big deal. So I divide the 150 kVA, which is the continuous current, the continuous kVA, thousands of volt amps, by the impedance, and I get 3000 kVA. So 3000 kVA is the short circuit kVA. And at 240 volts, that's 4.17 amps per kVA. We get 12,000 amps. Let's take another one. Let's choose a 500 kVA. 500 kVA, this time I'm going to choose a 208 volts. So this is a fairly common transformer at 208 volt. Again, I divide by 5%, get 10,000 kVA, and that ends up being about 28,000 amps. Let's go to 480 volt, 1500 kVA. This is a fairly common size 480 volt transformer. Same calculations, and we end up with a short circuit current of 36,000 amps. And one more, I'm going to look at a standby generator. This is a 500 kVA standby generator. You know, they come bigger, but that's a fairly big one. And we end up with 6,000 kVA. The reason why that's lower than the others is that the impedance is higher. So I've chosen an impedance of 12%. Alternators on generators are 12, 13, 14, 15%. So I'm going to make the statement that on electric circuits, you're probably going to have, there's 12,000, there's 28,000, there's 36,000, there's 6,000. You're going to have 10, 20, 30, 40, 50,000 amps is a typical short circuit current on a power distribution system. So question, how much current is in the average lightning bolt? Is it 30,000 amps? Is it 300,000 amps? Is it 3 million amps? Or could it be 30 milliamps, 31,000th of 1 amp? Think about that just for a moment. And the answer is 30,000 amps. Now, we just talked about the fact that in power distribution systems, you have 10, 20, 30, 40, 50,000 amps of short circuit current. Likewise, with lightning strikes, you have 10,000 amp strikes, you have 50,000 amp strikes with an average of about 30. How close do you really want to be to a lightning bolt? And many of us go through our whole career and maybe we see some sparks. We never really see a full lightning bolt and a full explosion. But anytime you're working on electrical gear, just remember you could have a full lightning bolt right in front of you. And if that doesn't scare you, then I think something's wrong with you. Now on the left, we have a bolted fault. Of course, no one does this intentionally unless you let an engineer go out and wire it. On the right is an arc fault current. So with an arc fault current, we've got something that shorts it, but then we end up with an arc. There is current in the arc, and therefore, excuse me, there's impedance in the arc, and therefore your arcing fault current is going to be lower than your bolted fault current. And we're going to talk about that coming up, but mostly next week, we're going to spend a lot of time talking about arcing fault current. In general, I've got arcing fault current is maybe 30 to 85% of the bolted fault current. This is human reaction to current. 10 milliamps is the let go current. Above 10 milliamps, you can't let go, and that's why our ground fault circuit interrupters will trip at about 5 or 6 milliamps. They are not going to protect you from shock, but they are going to trip before the current gets high enough that you can't let go of the wire. And then you can see the rest of them. 30 milliamps for stop breathing, 75 milliamps, your heart goes into fibrillation, and 5 amps, you get tissue burning. And a typical hairdryer takes 12 amps. So our bodies aren't very good, or maybe you could say too good of conductors of electricity, but they don't tolerate it very well. Now I love the next two little videos. I'm just going to play 2 videos for you today due to time. This one, we have intentionally shorted the 3 phases together, so when we energize it, we're going to have a bolted fault. Now, not knowing a lot about this, if I was not an electrician or an engineer, I'd say, well, that looks pretty scary, but I doubt that anyone would be hurt severely. Well, let's take a look in slow motion. Now, this is a different piece of equipment, but we're going to look at an arc fault in slow motion. The person standing there is a mannequin. He's going to stay there because he's tied off. But this, again, is in slow motion, so this will give us a little better feel for what's going on there. Now notice that he is clearly engulfed in flames. And so while we might think that the flame comes from the front, we're going to talk about just a little later the fact that you can get burnt with any exposure to your skin. And how long does it take to get 33rd degree burns? It's virtually instantaneous. And so that individual, any exposed skin or any skin that doesn't have proper arc flash protection on, is probably going to have 3rd degree burns. And as you know, there's no cure for 3rd degree burns. It requires skin grafting. What causes an arc flash? A lot of the things that I'm going to read are directly out of NFPA 70E, and you can see here in the lower right my reference. Usually an arc fault event occurs as a result of some movement, such as when a power circuit breaker is racked out, a conductor springs loose, a tool drops, an animal contacts an energized circuit part, a disconnect is open or closed, or a starter operates. Now, I put the bold here because I wanted to make a point of this. Most arcing faults are started as a result of human interaction, such as when a person blindly reaches into a cubicle containing energized conductors or circuit parts with a conductive object. Now, not all arc faults are caused by human interaction, but most are. This is, I think, a great slide. All of the things that are going on during of all, we have a 35,000 degree arc. Our copper vapor, copper solid expands to vapor. We get molten metal, pressure shock waves, deafening sound waves, shrapnel, hot toxic air, rapid expansion, and a blinding light. So a lot going on there. Now, just a couple of those things. How hot is 35,000 degrees? That's not something that I have a good feel for. And so the best example I have of that is that the sun's surface is approximately 10,000 degrees Fahrenheit. So that arc flash is 3.5 times as hot as the surface of the sun. And of course, you have a blinding light, and you have things that can cause third-degree burns almost instantaneously. Now, this has nothing to do with arc flash, but I think it's very interesting that the core of the Earth is about the same temperature as the surface of the sun. Next, we have an arc blast. We have a pressure wave that is up to 2,100 pounds per square inch. Our eardrum ruptures at 5 pounds per square inch. Plus, we get debris, projectile, molten material, and we can inhale some of that debris because when we're shocked, we tend to go and breathe in, and that's really a bad time for that. So not only are these things loud, but they actually rupture your eardrum. And you can tell that because of thunder. Imagine how loud thunder is when you're right next to it if you can hear it 10 miles away. This is copper to vapor. That copper some of it may go to liquid and end up as shrapnel or flying droplets of copper. Others actually vaporize. And when it vaporizes, that little piece of copper can expand 67,000 times its volume. So, example here, a piece of copper the size of a pea can expand to fill a freight car. So some of that boom explosion is air getting superheated, but some of it is metal, copper and steel and so on, turning from solid to vapor. And so that creates quite an explosion. By the way, you know what else expands about 67,000 times? Dynamite. Burns, I think most of you know this, but a superficial burn is your first degree. I tend to call that a sunburn. A second degree burn is going down into your dermis, and so you get blistering, and that makes me squeamish. That's horrible. If you go completely through the dermis, that's your third degree burn, and that's what requires skin grafting. Now, if you do arc flash, you probably recognize these numbers. If you don't, these are things that you really want to remember. A second degree burn is just curable. The skin bubbles at 1.2 calories per square centimeter, and you can get a second degree burn by exposing your skin to 176 degrees Fahrenheit for 1/10 of 1 second. A third degree burn, you have complete destruction of the skin, and that's 8 calories per square centimeter, and that is only 205 degrees for 1/10 of a second. So you can imagine when you have 35,000 degrees, third degree burns are pretty likely. So all of the arc flash standards are based around the 1.2 calories per square centimeter because we do not want you to get a second degree burn. And if you don't get a second degree burn, you're not going to get a third degree burn. So 1.2 is a very important number for us to remember. Now, what is a calorie? Right here in the middle, if you put your hand in the hottest part of the flame of a candle, not where he's got it, but down into the flame, and you leave it there for 1 second, that's 1 calorie. That gives us a feel for that. And 1.2 calories can give us a second degree burn. Okay, let's get into the regulatory requirements. There are 3 standards that are important to us. OSHA is what I call the big bad wolf. Those are the people who can fine you. Those are the people who can put you in jail. And I happen to be the proud recipient of a $50,000 fine from OSHA when I was the director of engineering for Geneva Steel, and we will get into that tomorrow. So OSHA is the one that has legal authority. Now below that we have the NESC, that's the National Electrical Safety Code, and that's strictly for utilities. We're not going to talk about that. We're talking about industrial and commercial during this presentation. NFPA 70E is for general industry, and we're going to talk a lot about NFPA 70E. And then IEEE 1584 has all the calculations. They've done tremendous amounts of testing, spent a lot of money in order to figure out how to do the calculations to give you the calories. And there are a few statements in IEEE 1584 that you're going to need to know, and so I'm going to tell you. NFPA 70. NFPA 70 is the National Electrical Code. It's been around for a long time, 1897 to be exact, and it's gotten a little bit thicker since then. And it's a very good book. If you ask somebody on the street, have you ever heard of the National Electrical Code? Oh yeah, they know about it. And if they see something that looks dangerous, they might say, oh, that doesn't look code, even though they don't have any clue what the code is. Well, and that protects users of distribution systems, users of electricity. What does it not protect? It does not protect maintenance people or electricians maintaining or installing electrical systems. And it is those people who frequently are hurt. So OSHA went to NFPA and said, will you add on to your booklet, it's not a booklet, but it's huge, another standard to protect electricians and electrical workers? They did, and they gave it the same number. It's NFPA 70, but this one is NFPA 70E. It is the Handbook for Electrical Safety in the Workplace, and it came out in 1979, whereupon we all ignored it. And over time, the OSHA and electrical inspectors have gotten a lot more serious about enforcing that. And at this point, there's a lot of interest in it, and OSHA's finding people, and everybody's knowing about it, which is an indication of the interest we get in this, because you do have to know it. This, the National Electrical Code, the current version is 2020, but I left the 2017 in there because the NFPA 70E comes out exactly 1 year after the National Electrical Code. So the current version of NFPA 70E is 2018, which came out 1 year after the 2017 National Electrical Code. Of course, the current version of the National Electrical Code is 2020, and the next version of NFPA 70E will be 2021. So this presentation is fully up to date on NEC or NFPA 70E, the 2018 version. What is covered in NFPA 70E? Employee workplaces that include the installation of conductors and equipment that connect to the supply of electricity. So basically, if it's an employee workplace and you have electricity, then you are covered by NFPA 70E and you have to comply with it. You'll be happy to know that in your house, since that's not an employee workplace, this doesn't cover your house. Although, if you want to get picky about it, the standard says that if you put a home office in your house, it becomes an employee workplace and you are covered. But I don't know of any time OSHA has gone out to people's houses in order to fine them based on non-compliance with NFPA 70E. On the front cover and the back cover of the new NFPA 70E, new meaning 2018, you have this. And this is basically an acknowledgement by the authors that they cannot protect you using PPE alone. And so we're not going to spend a lot of time on this, but suffice it to say, they want you to start from the top of their pyramid, eliminate the hazard if you can, if not substitute it, replace the hazard with something less hazardous. Then engineering controls, awareness, administrative controls, and only work on things hot with personal protective equipment when those other things fail. So we could spend a lot of time on that, but we just don't have time today. Now this is OSHA. This is very important. Employees must be provided with and must use protective equipment that is appropriate for the specific parts of the body to be protected and for the work to be performed. So it says employee must be provided with. Who must provide them with? The answer is their employer. So OSHA is very strict about this. Your employer is responsible for providing you with proper PPE. However, then there's those next three words, and must use. OSHA can actually fine you, jail you, if you have received PPE, you've been trained in PPE, but you've refused to wear it. Energized work conditions. So energized electrical conductors and circuit parts operating at voltages equal to or greater than 50 volts shall be put into an electrically safe work condition before an employee performs work if any of the following conditions exist. The employee is within the limited approach boundary, which we'll talk about shortly, or you're interacting with equipment where there's a danger. So what is the electrically safe work condition? Well, that's lockout, tagout. And I think all of you who have to work on electrical equipment are pretty familiar with lockout, tagout. So I'm not going to spend much time on that. Now, if you are less than 50 volts, you don't need to wear PPE. Energized electrical conductors and circuit parts that operate at less than 50 volts shall not be required to be de-energized. So if you're under 50 volts, then it's safe, right? Well, actually, no, that's not at all right. Here is a battery room. You can get more than 5,000 amps out of a battery, and clearly that's not safe. Well, it turned out that I didn't finish the paragraph. It said, shall not be required to be de-energized where the capacity of the source and any overcurrent protection between the energy source and the worker are considered, and it is determined that there will be no increased exposure due to electrical burns or to explosion to electric arcs. So basically they're saying if it's less than 50 volts, we leave it to you to determine the hazards. If you're looking at a 4 to 20 milliamp speed reference on a variable frequency drive, I'm not going to worry about de-energizing that to work on it. But if you have things that have a sufficient danger, such as a battery room, then you need to take precautions. But that is the 50 volt rule. Energized work. Can you work energized? Because we just said that you can't. We just said that in order to work energized, you must lock and tag out that piece of equipment. Well, it turns out there are two and only two situations in which you are allowed to work energized. First is additional hazards or increased risk. So an example of this might be a hospital emergency room. You go in there and you say, hey, I need to take an outage for an hour because I need to maintain some electrical equipment. Well, that puts people in danger. Second is infeasibility. Clearly, if you're going to start up an electrical frequency, a variable frequency drive, you're going to do troubleshooting. A lot of times you have to have it energized in order to do your troubleshooting or do your startup. And in that case, OSHA allows you to work energized. Here's qualified person and unqualified person. A qualified person is one who has demonstrated skills and knowledge related to the construction and operation of electrical equipment and installation and has received safety training to identify the hazards and reduce the associated risk. I like the definition of unqualified person. It is a person who's not a qualified person. Now, what does it take to be qualified? When we give our full arc flash class, we give a certificate and then you're qualified, right? Wrong. It takes three things to be qualified. Number one, you have to be trained on this standard, NFPA 70E Article 100. Number two, you have to have the appropriate background, and that generally is an engineering or an electrical degree of some sort, and the experience to be qualified to work on that type of equipment. And the third thing is an understanding of the thing you're working on. So if you're an electrician, you're fully qualified, you've had years of experience, maybe you're even a master electrician, but you do houses and you wire houses. And then somebody says, can you come into this industrial plant and work on this electrostatic precipitator? The answer is no, you're not a qualified person. You must understand the piece of equipment you're working on in order to be qualified. Retraining must occur every 3 years. So according to OSHA, you must be retrained. How do we know that you've been retrained? Because you have to have a certificate written that shows you've been retrained. And the retraining that we're talking about here is NFPA 70E. So anybody that works on electrical systems should be retrained a minimum of every 3 years, something you need to be aware of. What is the arc flash boundary? Well, that's where you have 1.2 calories per square centimeter. And that is the point where you can get a second-degree burn. So basically, if you're outside the arc flash boundary, you're safe from getting a second-degree burn. If you are inside the arc flash boundary, then you could get a second or a third-degree burn. How do you know where the arc flash boundary is? That's the purpose of an arc flash study. What is the limited approach boundary? It's an approach limit at a distance from an exposed energized electrical conductor or circuit part within which a shock hazard exists. What is the restricted approach boundary? It's an approach limit at a distance from an exposed energized electrical conductor or circuit part within which there is an increased likelihood of electric shock due to electrical arc over combined with inadvertent movement. If this is the first time you're hearing these approach boundaries, I don't think those are really definitions that really tell me what's going on here. And so I'm first of all Let me come back to this slide in a minute. I'm going to talk about the old standard. Now, this standard was in 2009. This changed in 2012 and 2015. And 2015 was really when they eliminated the prohibited space. 2012 was when they changed the requirements for arc flash clothing. I'll talk about that in a minute. So take a look at this. We've got a flash protection boundary. The flash protection boundary is the point at which you could get a second-degree burn. Then we had the limited approach boundary, the restricted approach boundary, and the prohibited approach boundary. When you cross the limited approach boundary, you're in the limited space. When you cross the restricted approach boundary, you're in the restricted space, and so forth. Now, the way I remembered these was, this is your visitor boundary, this is your helper boundary, and prohibited is your worker boundary. So if you just want to come in and look and talk to the people doing the work, you should not cross the limited approach boundary unless you are qualified or with a qualified person. In order to cross the restricted approach boundary, you're going to be a helper, you're going to be holding tools, you're going to be holding meters, and you cannot cross that unless you're qualified and have the appropriate PPE for shock protection, not burn protection, but shock. And the prohibited space is for the person who probably is going to actually touch the live part. And so that person must be qualified and must have the appropriate PPE. Now in 2015, they said, is there really a significant difference in the danger level for the helper and the worker? And they decided, no, there isn't. And therefore they eliminated the prohibited approach boundary. So now I just have the limited approach boundary, which is for the visitors or bosses or what have you. And then the restricted approach boundary, which is for both the helpers and the workers. The reason I state this is that once you put an arc flash sticker on, you never need to change it. And therefore you are going to see arc flash stickers that have the prohibited approach boundary, and you need to know what that is. And you simply ignore that boundary. Where do you find these boundaries? You find them in NFPA 70E in table 130.4DA. And here you have our voltages, and here's your limited approach boundaries. Now I'm going to focus on this right here, 151 volts to 750 volts. So that covers your 12240, your 12208, and your 277 480 and your 480 delta systems. All of those are in that same category. If you have an exposed movable conductor, like an overhead line, your limited approach is 10 feet. If it's a fixed circuit part, your limited approach is 3 foot 6 inches. So I'm going to talk about the 3 foot 6 inches. It's important that you know that. And the restricted approach is 1 foot. By the way, the prohibited approach used to be 1 inch. And of course, that isn't valid after 2015, but may still be on the sticker. Here is I'm going to go over this just one more time. The arc flash is the burn boundary. That's the point at which you could get second-degree burns. If any work is going on, you must not cross that without burn protection. The limited boundary and the restricted boundary are shock boundaries. You can only cross the limited boundary if you are qualified or with a qualified person, and you may not cross the restricted boundary unless you are qualified and have appropriate PPE to protect you from shock. You also have to have a work permit. When don't you have to have a work permit? If you're doing testing, troubleshooting, or voltage measuring, you don't need a work permit. If you're doing thermography, ultrasound, visual inspections, you don't need a work permit. If you're just going through the area or doing general housekeeping, you do not need a work permit. However, any kind of major work, you need a work permit. And there, you may have an electrical hot work permit that's already in your facility or for your company. If you don't, there's a work permit right in NFPA 70E. You can just put that on the copy machine, copy it off, and use it. But clearly, for most of what we do is testing, troubleshooting, voltage measuring. We do not need a work permit. Now we're going to get into labels and then PPE. That's the two areas that we have left. Notice at the bottom here, this is IEEE 1584.1. Where do you need labels? As required by codes and regulations, labels should be created and affixed to electrical equipment. This equipment should be included as a minimum switchgear, switchboards, panel boards, industrial control panels, meter socket enclosures, adjustable speed drives, machine control panels, and motor control centers. So if you say, oh, we have a policy here of not putting the stickers on our adjustable frequency drives. I'm sorry, guys, you can't do that. You don't get that choice. It says, as a minimum, you must include those things. And generally what they're trying to do is put a sticker on anything they think you're going to open up and work on hot. Now, transformers, motors, bus, motor terminal boxes, you can label those if you want, but you are not required to. Equipment labeling. These are the things that need to be on the equipment label. That's right out of NFPA 70E. I have never seen an equipment label that contains only those things. Most equipment labels have more than this on, but this is the bare minimum. This is an equipment label. So let's take a look at it. They tend to all look fairly similar. They have this yellowish top, or if it's over 40 calories, a lot of times people will put a red up there. Arc flash and shock risk, we have 21 calories at 18 inches. Well, what is 18 inches? That's called the working distance. And the working distance is the place where your face and chest area, it's about how far they're going to be away from the energized part. That's decided for you. For 480 volts, 208, 240, it's 18 inches. The standards decided that for you. 21 calories, obviously dangerous. We have 130 inches is your arc flash boundary. So that's quite a ways, more than 8 feet. This is 480 volts. There's your glove class. And here's your limited approach boundary. That's 3.5 feet. That's correct. And your restricted approach boundary is 12 inches. And then, of course, we have the location and we have the circuits that protect it and the company that did the study and so on and so forth. All right, in 2015, they made these changes. Number one, they formalized 2 different ways of selecting PPE, which we will go over. Number 2, they eliminated hazard risk category 0. You may find on stickers, it's still saying hazard risk category 0. We kind of ignore that, but hazard risk category 0 was basically those places in which there was no risk of a second-degree burn. Next, they changed hazard risk categories to PPE categories. Oh, thank you very much. So that makes it a little bit more confusing. Those are the same thing. And many times you will see HRC, that means hazard risk category. A lot of your older stickers are going to say HRC. Newer stickers will say PPE. It's the same thing. And admittedly, I like the PPE categories better because I think it's a little bit more obvious what they're talking about. But you just need to realize that those are the same thing. Number 4, we eliminated the prohibited boundary. Now, this is important, and I don't have a lot of time to put on this, to talk about this, but this is called the likelihood of occurrence. And if in the standard, it'll say, if there is a likelihood of occurrence, you need to wear PPE. So if you're going to read a panel meter, is there a likelihood of occurrence? No, therefore you don't need to have PPE. If you're going to operate a circuit breaker, switch, contactor, or starter, is there a likelihood of occurrence of an arc flash? No, so you don't need PPE. If you're going to open up a hinged door, yes. Now this is an interesting one that a lot of people don't realize. If you're going to perform infrared thermography and other non-contact inspections outside the restricted approach boundary, now the restricted approach boundary is 1 foot, that would say no. So that's very interesting. If all you're doing is going in to take infrared pictures, to look, you don't need PPE there. But notice that it says this activity does not include opening of doors or covers. The next one is if it's only 120 volts, then you don't need your PPE and so forth. Now, I've just put a few rows in here. This table is actually much longer than what you see on the screen. Okay, there's 2 ways to do this. There's the incident energy amount analysis method, and there's the arc flash PPE category. The one prior to 2015 was the arc flash PPE category. I'm going to call that the old method. The one 2015 and later was the incident energy analysis method, so I'm going to refer to that as the new method. So here is the PPE category. It used to be called hazard risk category. And up to 4 calories, you needed to wear arc-rated long sleeve shirt and pants, or arc-rated coveralls, arc-rated face shield, or arc flash suit hood, and as needed, arc-rated jacket, parka, rainwear, hard hat liner. Plus you needed your other equipment, your standard safety equipment, hard hat, safety glasses, and so forth. This was a change in 2012. In 2009, this used to say fire-resistant clothing, until they found that some fire-resistant clothing burst into flame in a 35,000 degree arc. So they changed it. After 2012 and later, you must wear arc-rated clothing, not fire-resistant clothing. Now, if you have some clothing and on the inside there's a little tag and it says fire-resistant, that does not necessarily mean that it is not arc-rated. It could be fire-resistant and arc-rated, but you may not wear clothing that is only fire-resistant. Up to 4 calories, that's category 1, and so you have to wear category 1 gear that will protect you up to 4 calories. Category 2 is 8 calories. What is the difference between category 2 and category 1? There's only 2 differences. One is category 1 is 4 calories, category 2 is 8 calories. The second one is this. You must have an arc-rated balaclava. Now, what is a balaclava? Well, that's that little dessert you get at Greek restaurants. Oh, wait, no, that's baklava. Sorry, this is a balaclava, and over here is your balaclava. Now, you saw the picture. You see this guy here? Can you see bare skin? Guess what? If you walked around, you could see his neck, you could see the back of his head. If there's an arc-rated explosion there, he's going to get burnt, isn't he? So why don't they require an arc-rated balaclava here? And my answer is because they screwed up. That's my opinion. Now, this does say 4 calories, so it will not give you a 3rd degree burn, but it will give you a 2nd degree burn, and this is crazy. So they have fixed that. Most people do not have category 1 and category 2 gear. They simply buy category 2 gear, and then they use that when they're working on either category 1 or category 2 systems. What happens when you go to 8.1 calories? Now you need an arc flash suit, also called a beekeeper suit or a Buzz Lightyear suit. And these things you can only work about 15 minutes at a time. Category 3 gives you 25 calories, and category 4 is 40 calories. And I don't know of anybody, although I'm sure there are some people who have category 3 arc flash suits. We don't. We only have a category 4 arc flash suit. And then we use it in category 3 or category 4 systems. Now, what if it's over 40 calories? What if it's 40.1 calories? The answer is you can't work on it. Here's an arc flash suit, and there's a fan that you can get for that arc flash suit that'll make it slightly more comfortable. Next is the incident energy analysis method. This is the new method. I think this new method, they recognize some of the shortcomings of the old method, and therefore they introduced the new method. You can use either method, but I believe this is going to be taking over, and at some point they may discontinue the old method, but we only use this method. Below 1.2 calories, you're not at risk for a 2nd degree burn. Therefore, just shirt and long sleeve shirt and long pants or coveralls, but they must be non-melting or untreated natural fibers. This is under 1.2. When you get 1.2 to 12, now you need your coveralls, and notice that they've fixed the balaclava problem. Anytime you're over 1.2 under the new system, you must wear a balaclava. And it is our company policy to wear a balaclava all the time when we're working on energized parts. Also notice that this allows you to go up to 12 calories. So under the new method, you can go to 12 calories. Under the old method, only 8 calories. But again, if you're going to go to 12 calories, you must have shirt and pants or coveralls that are rated for 12 calories. Above 12 calories, you have to have the arc flash suit. Now, notice the old method, you could go up to 40 calories. In the new method, there is no limit. You can go as high as you want in calories as long as you have an arc flash suit rated for that number of calories. Well, does that mean we have arc flash suits rated for more than 40 calories? Yes, we do. These particular arc flash suits are Salisbury, and you can see that they have a 15, 25, 40, 65 and 100 calorie arc flash suit. I personally am not aware of anything over 100, but I suppose it is possible. This is a poster that we have when we do an arc flash study. We typically provide these posters to the customer, and they're about 11 by 17 plastic. They're sunlight resistant, and they show you they're based on the new method under 1.2, 1.2 to 12, and over 12. And it shows you a picture of how the people are dressed. And then down here, it shows you what you need to wear. This is our arc flash label. And you can see on the left, we have our burns. And on the right, we have our shock. We also have a QR code. If you scan that QR code, it takes you to this. And so every time new arc flash standards come out, we will update this to make sure this complies with the latest of the arc flash standards. And we're back to this. So what do you need to wear here? If you come in here, there should be an arc flash sticker. If there isn't, you should assume that it's a PPE category 2. Make sure that you wear a balaclava, face shield, glasses, hearing protection, and so forth, and gear that's rated for at least 8 calories. All right, last slide here is the moral of the story. You should know the equipment you're working on and the hazards involved. Don't work on anything that you're not comfortable with, and follow the OSHA safety standards. Now, next week, we're going to pick up where we left off this week, and we will get into much more detailed analysis and talk a little bit about how you do arc flash mitigation. In other words, reducing the calories on an existing system in order to make that system safer, or to make it so that you can wear coveralls rather than an arc flash suit. We'll also get into coordination issues. We'll talk about arc flash currents, and we'll talk about a lot of details such as fuse coordination with arc flash, our ARMS circuits, or ERM circuits, that's the arc flash reduction maintenance system, and so on. So that's it. Please feel free to type in any questions, and we'll be happy to answer them now. But that completes our presentation for today.
Great, thank you. All help field questions. We've had a couple come in. If any of these are covered in the future training, Craig, just go ahead and feel free to say that. The first one I see is how to calculate incident energy.
Yeah, so I took the slide out of here. If you want to calculate the incident energy, the formulas are in NFPA 70E. And I had a friend who's an engineer, and he didn't have the arc flash program. And so he said he was just going to go in and do the calculations by hand. And I asked him after he was done how it went, and he said, never again. So basically, the formulas are in there, but they're horrible. And the chances of you getting through there without making a mistake are almost zero. So basically, what I'm going to tell you is there's only one way to calculate arc flash energy, and that is to have an arc flash program such as Easy Power or SKM, or one of those that has all of these equations in there. The equations that we use, that almost everyone uses, comes out of IEEE 1584. And you really need that program in order to do the incident energy calculations. Now, if you want to have a full arc flash study done, you can hire a company like ours to come out and do the whole thing. If you decided you wanted to do that and you were going to go take pictures of all the breakers, figure out how long the cable is from here to there, get the utility transformer and the utility short circuit current and so on, and you wanted to bring that in to somebody like us who has the program, and the program's pretty pricey, it's what, $10, $15, $20,000, then that certainly saves you a lot of money. But my advice is you really have to have the program to calculate the incident energy.
Great, thank you. We did have one question about if EMC provided an arc flash study, which you answered during that. We do have 3 people who have asked if we will be providing a recording. I can go ahead and answer that, but we will send that out within the next day or two with a link to the recording and any related documents. Next question that came in is, how often does an arc flash study need to be completed?
Now that's an excellent question. We discussed the fact that you need to train your people every year. Excuse me, every 3 years. Sorry, every 3 years. How often do you need to do an arc flash study? The answer you must evaluate your system every 5 years. Now, let's say I walk into my plant, I look around, and it's got the same switchboard, the same transformers, everything as it did 5 years ago. Then you're done. That's it. You have evaluated your system. You do not need to do anything different. And you never need to change an arc flash sticker as long as that arc flash sticker was valid at the time that it puts in, that you put it on. So the only time you need to do an arc flash study is when you change something. And even then, you don't need to do, excuse me, an arc flash study for the whole plant. You don't need to redo everything you've done. All you need to do is add the parts that have changed, have the computer recalculate it, and put stickers on any parts that have changed. But you are never required to go through and do a complete arc flash study, other than the first time.
Great, thank you. We do have another question. What about arc flash for utilities?
Yeah, now arc flash for utilities, and I'm sorry to say this, but I don't know utility systems, and so this is all part of the National Electrical Safety Code, and I just don't know. Now, if the utility has an office building, or if the utility has a shop or something like that, then they're subject to exactly the same requirements that we've just talked about. What the utility is exempt from is their transmission and distribution system. So I don't have anything that I just don't know about the rules and requirements for utility transmission and distribution systems.
Great. We do have another question. Does the evaluation include some sort of inspection like opening panels, etc.? Does the available current at the transformer change that evaluation?
Yeah, so definitely the available current at the transformer does change that evaluation. And let's just assume as an example, you've got a 1,000 kVA transformer, and you you do your arc flash study, and then you need more power, and so you come in and put a 2,500 kVA transformer in there. Well, that changes everything, but it doesn't mean you have to go through and redo all the things you did originally. If you still have certain switchboards and panel boards and so on, and cables that went from one place to another, you've already got those. They're already in the system. So all you need to do is change the transformer size, and then that probably means that you added a new switchboard. So you just add those two things to your existing database. Boom, you have the computer, and it takes 2 or 3 seconds, and then you take a look at it, and if it has changed the arc flash, which it will have pretty seriously, then you need to put more stickers on. But it's a lot easier than going through and doing that first arc flash study. Now, I want to mention here that next week we are going to talk about this some more. You may find that when you put up a 2,500 kVA transformer instead of a 1,000 kVA transformer, that the calories go down. And that doesn't seem to make a lot of sense. But we are going to discuss that in a lot of detail. Even though it seems like the higher the short circuit current, the more dangerous it is, that is not always the case. So please come back next week, and we're going to talk about that in more detail.
Great. Next question is, do you have to have a study done, or can you just use the tables provided in NFPA 70E?
Yeah, so we didn't talk about that because of time, but there's 2 methods for selecting PPE. There's the old method and the new method. And if you want to use the PPE categories method or the old method, there is a table in there. And if you want to use those tables, you can use those tables, absolutely. Now, notice that the tables say that your fault generally can't be over 25 KA in some instances, in other instances, 65 KA. So you still need to know your breaker opening time, and you need to know your short circuit current. So it's not as easy as it sounds. you are going to have to know those things, and that's going to require you to look at your circuit breakers, see if those are instantaneous trip circuit breakers versus time delay circuit breakers, and you're going to have to know your short circuit current. And so you don't necessarily need to do a big arc flash study to get the short circuit currents, but it's pretty important that you know that. And so in my opinion, can you do that? Yes, they're still allowing you to do that. Is it a smart idea? I would say it generally isn't a very smart idea, but those tables are in there and they're in NFPA 70E, and that is still valid. You can still do that if you want.
Okay, it looks like we have one last question here. Or a couple came in. Do arc flash differ inside and outside?
Now, say that again. Do arc flashes differ inside and outside?
Yeah, that's what they asked.
Yeah, no, same thing. It's the same thing whether you're inside or outside. Now, as we talked about on the limited approach boundary, if you go outside and you've got a cable, let's say, going from your building to the utility pole, well, that cable can swing, and therefore we call that a movable conductor. So now your limited approach is 10 feet rather than 3.5 feet. But no, the rules are all the same outdoors and indoors.
Great. Is there a time frame or certification of stored PPE clothing?
Yeah, there is. And that's something we were going to get into next week, is how you maintain your PPE clothing. This sounds like a chicken answer, but I'm going to give it anyway. The time is based on the clothing manufacturer. So there's nothing in NFPA 70E that says how you have to launder your clothing, or when you have to replace your clothing, or at what point that clothing no longer protects you. They leave that up to the manufacturers. So when you get your clothing, please do pay special attention to that. They will tell you how to launder it. Laundering of PPE clothing is very, very important if you want it to maintain its calorie level. And so you want to launder it properly, and it will tell you how long it will last. And we are going to talk about that next week a little bit, but the answer is still going to be the same, is that depends upon the clothing manufacturer.
Great, that looks like all the questions. So we'd like to thank everyone for joining us today. We look forward to seeing you next week. Thanks.